Hello everyone, my name is Hyunjong Choi from University of California, Riverside. Today I'm going to talk about a new design of the second version of Robot Operating System. ROS is a flexible framework for writing robot software and one of the most popular open source in academia and industry. This figure was captured in April this year. As we can see, the number of users of ROS is still increasing for different metrics since it had been introduced in 2007. This is because ROS has a strong software modularity. It provides lots of software tools, libraries, and best practices across a wide variety of robotic platforms, so developers can easily build a software stack to fit their own robots. However, over decades, the first version of ROS has exposed the limitation, especially in real-time support. Then, why is real-time capability important in ROS framework? There is a good example, which is AutoAir. AutoAir AI is all-in-one open-source software for autonomous driving technology that is built on ROS1. On top of ROS as a middleware, AutoAir consists of individual modules in an application layer, such as sensing and perception, planning, and control. And those modules are connected with data dependency and forms a processing chain. Let's suppose this system cannot guarantee the required timing constraint. For example, the end-to-end latency of the perception pipeline is not predictable. If it is, this may cause a catastrophic accident of the vehicle. So real-time support is a key factor for timing and safety-critical application on ROS framework. This motivates the development of second generation of ROS in the community. ROS2 has released its first long-term support version in 2017. Although most concepts are inherited from the original ROS, ROS2 has completely refactored the original ROS framework. And moving from ROS1 to ROS2 has many benefits related to real-time capability, quality of service, and security. And ROS2 supports DDS, which is an industry-standard real-time data distribution service. However, ROS2 still suffers from priority inversion of callback because timer callbacks always schedule first. And the existing analysis framework is too complex and pessimistic. And also, so far, there is no study for systematic resource allocation policy for ROS2, especially in terms of end-to-end latency of chains. So, to the best of our knowledge, our work is the first study of redesigning ROS2 scheduler to improve end-to-end latency of chains. Here are the contributions of our work. First, we propose a new priority-driven chain-aware scheduler for ROS2 in multi-core environment. We also developed the analysis framework to upper bound end-to-end latency of chains under the proposed scheduler. We implement our scheduler running on ROS2 in an embedded platform and conducted case studies and other evaluations. Before introducing our scheduler, I would first explain more about ROS2 architecture as a background, especially what are scheduling-related abstractions in ROS2 and what are the challenges from them. Basically, ROS2 consists of multiple layers such as application, ROS client library, ROS middleware library. And what we are interested in is fundamental scheduling-related abstractions across those layers. First, there exists a callback. Callback is a minimal schedulable entity in ROS2. We model the real-time callbacks either a timer or regular callback based on whether it is triggered by a timer or external events. And callbacks are non-preemptive within an executor. Node is a collection of callbacks and node is minimum allocation unit to executors. Then these nodes are allocated to an executor, which is OS level schedulable entity running on CPU core like a thread. So executors are preemptible. In our work, we modeled the executor as a thread, so we schedule executors with sched_FIFO, which is a real-time scheduling policy in Linux. On top of these scheduling-related abstractions of ROS2, there is a chain. We define a chain model as a set of callbacks, and this model actually has been widely used in prior work to analyze the end-to-end latency of tasks with data dependencies. We assume that the start callback is a timer callback and others are regular callbacks. And we also assume that the chain has a semantic priority given by system designer based on the criticality in the system. So the scope of our work is how to schedule and allocate schedulable entities to improve latency of chains. With these scheduling entities, what are challenges in ROS2? In order to find that, we first conduct a simple experiment. We used two safety-critical chains using 10 callbacks and assumed that chain 1 is more critical. Here tau 1 and 4 are timer callbacks and they arrive at every 1 second. All others are regular callbacks and triggered by its prior callback. First, we perform the case where all callbacks are in a single executor. As discussed in the latest work, ROS2 has a unique scheduling behavior within executor as timer callback always scheduled first. We also have observed this behavior in our experiment. For example, here tau 4 executes first whenever it is ready. This actually makes the other regular callbacks priority ineffective. Therefore, as we can see in this table, ROS2 results of fairness-based scheduling, and this can jeopardize the timeliness of safety-critical chain. At this time, we allocate the callbacks of each chain to a separate executor. Actually, there is no guideline to assign priority of executor in ROS2. However, in an intuitive way, we can allocate all callbacks of chain 1 to the highest priority executor, because chain 1 is more critical than chain 2. Therefore, as you can see in this scheduling, chain 1 always preempts chain 2. However, this method does not resolve the problem because chain 2 results unexpected high latency. This is mainly because for a chain, a prior chain instance interferes other instances that were released later. This is like a self-interference. So priority assignment for executor is another challenge in ROS2. Now I introduce our new priority-driven ChainAware scheduling on ROS2. Based on the observations in the previous slide, we redesigned default ROS2 scheduling architecture with two considerations. First, higher semantic priority chain executes first to avoid fairness-based scheduling. Second, for each chain, each instance on the same CPU executes in arrival order to prevent self-interference. Especially for the second consideration, we state desired properties as lemma 1. This lemma describes the conditions for prior chain instance guarantee to complete before a new chain instance starts its execution. Basically, the idea is that priority of callbacks of a chain is in reverse order. If it is, a newly released chain instance cannot interfere until a prior chain instance finishes its execution. Using lemma 1 as a pillar, in this slide, I will explain scheduling strategy for our scheduler. We consider scheduling strategy in two aspects: chains running within executor and across executors. Strategies within an executor tell us how callbacks of chains are scheduled in an executor. And we propose four strategies based on our classification of chains and callbacks. Strategies are designed to satisfy our design goals in the previous slide. So priority of high-indexed callback is higher than low-indexed callbacks. And if there exists multiple chains, we assign higher priorities to callbacks from that are more critical chain. In addition to four strategies, we propose two more strategies for chains running across executors. We keep the same principle as the above, but this time we define executor's priority to satisfy our design goals. To realize the scheduling strategy in a previous slide, we found solutions in two aspects. First, a priority assignment of callbacks, and second, node allocation. Priority assignment of callbacks can be done intuitively to realize scheduling strategies. We first sort change in an ascending order of semantic priority, then assign priority to a callback from low priority number to high. Then we propose chain-aware nodal allocation algorithm. This scheme allocates given nodes to executors and then maps those executors to available CPU cores. The algorithm also designed to minimize interference between chains by allocating all nodes associated to one chain to the same CPU core whenever it is possible. The diagram illustrates the flow of our algorithm. Basically, it starts sorting nodes and allocates a node that is associated with a more critical chain first using higher priority executors, and consists of three parts. In part A, sorted nodes are allocated into an empty executor, and then that executor is allocated into feasible CPU core. If there exists no empty executor, we found feasible executors that are already mapped into CPU core in part B. For each part, we make sure that the scheduling strategy should be satisfied. If a node cannot be allocated by part A and B, that node is handled in part C. So far, we explained the overall design of our new scheduler. Now, we run the same workload set at page 7 using our proposed scheduling framework. For both cases, we have observed that the first chain, which is a more critical chain, always executes first. So we can say that PiCAS does support priority-driven scheduling, not a fairness-based scheduling. And also, prior chain instance always completes its execution before newly released chain instance starts, which supports chain-aware scheduling. Based on these results, we can say that the PiCAS outperforms ROS2 default scheduling significantly in terms of end-to-end latency and also overcomes the aforementioned challenges. Our scheduler is also equipped end-to-end latency analysis framework. In this slide, I will briefly explain how our analysis framework works. First, since our framework targets on multi-core system, we consider a subset of a chain on one CPU core as a single artificial callback for the analysis purpose. So there may exist multiple segments if a chain executes over multiple CPU cores. With this concept, our analysis consists of two steps. First, computing the worst-case response time of each segment of a chain. Then in a second step, we add up the worst-case response time of all segments for the same chain to get the latency. Now evaluation. The evaluation is performed in three ways: case studies, schedulability analysis, and analysis learning time. In this presentation, I will show parts of the result, those underlying the evaluation, and more evaluation results are on the paper. We implement our scheduler in ROS2 Eloquent version, running on Ubuntu in NVIDIA Xavier platform, and compared three different approaches. First, ROS2 is ROS2 default scheduler which has no analysis. ROS2 SD is the latest work that models ROS2 scheduler as a resource reservation and has its latency analysis framework. Then ROS2 PiCAS is our new scheduler with the proposed analysis framework. In order to test practical effectiveness, we use a case study that is inspired by indoor navigation stack of F1 test vehicle. The workload for our case study consists of 6 real-time safety critical chains and another 6 best efforts chain in 4-core environment. And we assume that low-indexed chains are more critical. This is the result of our case study. The first figure shows the measured end-to-end latency of chains in a box plot. As we can see, the purple color represents the result of PiCAS, and it outperforms the others on most real-time chains. But as the semantic priority of chain is getting low, the latency of PiCAS is not better than the others and even worse. This result actually what we expected because PiCAS can schedule change while respecting change semantic priorities. So we conclude that our scheduler has a significant benefit in end-to-end latency for safety-critical chains. The below figure shows the maximum observed latency and the analyzed latency. And the result represents that our latency analysis provides tighter upper bounds for real-time chains. In our paper, we have more evaluation results that conducted in more complex scenarios. We also conducted schedulability experiments. For this experiment, we used 1,000 randomly generated workload sets for 3 different target utilizations in 4-core environment. Each workload set has 45 callbacks that forms 9 chains. We also assume that a low-index chain has higher semantic priority. And as we expected, the ROS2 PiCAS significantly outperforms ROS2 SD for all utilization setups. Especially on the ROS2 PiCAS, the first 4 chains are always schedulable because they are allocated to the highest priority executor on a different CPU core by our allocation algorithm. And also, since ROS2 PiCAS prioritizes chains based on their semantic priority, the schedulability ratio decreases as the chain's priority is getting low. Here is the conclusion. In this work, we propose a new priority-driven ChainAware scheduler with its end-to-end latency analysis framework for ROS2. Our experimental results represent that the proposed scheduler outperforms the existing ROS2 scheduling with respect to end-to-end latency under practical scenarios. As a next step, we are planning to deploy our work to more complex and practical scenarios, such as AutoWare.auto, which is autonomous driving software built on ROS2. Thank you.